Let's look at a 1-bit ADC first of all. And just like in the case of DAX, even though a 1-bit ADC is not usually used, it just helps us to understand what ADCs do, and it helps us to really grapple with some of the issues that are involved in designing the ADC. A 1-bit ADC is basically a comparator, as is shown on the screen. So you have an analog input here, and here's a comparator, and it compares whether the value is below 0 or above 0. If it is above 0, the comparator just gives you a high, a logic high. If it is below 0, it gives a logic low. That's basically a 1-bit ADC, right? You just compare. So another way of saying it would be a 1-bit ADC divides the whole range of the ADC into how many parts? Two parts, right? 0 and 1. So basically, if you compare it with the middle of your range, if it is lower than that, you give a low SN output. If it is higher than that, you give a high SN output. Usually, however, uh, uh, what we do is we put a little bit of hysteresis in the comparator, just so that you don't get a lot of bouncing at the boundary, right? So when you're going, so your instead of your characteristic being a rise at 0, you have a characteristic that rises like this. You have to go a little above 0 so that you get a high, and if you're coming from the high, you have to go a little below 0 to reach back into the low part. Okay, in a ADC, usually you have a latch. We've already looked at what latches are in Medical Instrumentation 1, so you know that. So here's a comparator. So the entire ADC, here's a comparator. The comparator gives an output high, and then that is stored by the latch for some time, so that the succeeding circuit can have it stored for some time. Okay. Now, the problem with using comparators, the major problem, is that we have something called metastability issues. And this issues comes as a result of the fact that depending on what kind of voltages are applied here, the output changes slowly or fast. Let's take a look at that. So look at this upper graph first. On the x-axis, we have time, and on the y-axis, we have the comparator output. Now, if the differential voltage that you're giving to the comparator is very high, then the output immediately goes into a high, right? So it's at low, the output is at low, and now you're giving a large difference, and so the output immediately goes high, and that's what you want. But if you have a small voltage, the speed of rise would actually decrease. It will go slowly. And what happens if you have a zero VN? It may still rise, but it will rise very, very slowly. Okay. So and if you are applying a latch signal at the output, and let's say you apply the enable latch at this point, with a large VN, you have already reached the final state. Uh, However, in the next two cases, you have not reached the final state, and you are in some kind of an undefined territory. You are neither at logic 0 or neither at logic 1. And this issue gives rise to a lot of problems with analog to digital conversion, especially because when we are using these comparators to do analog to digital conversion, we are usually trying to make the comparators work as fast as possible. But then the speed is limited by this kind of metastability issues.